So this video will go over chapter 6 and section 6.1 on energy. So to study how matter behaves, a chemist must study the atoms and molecules that compose matter. And here on the left side you have atoms, carbon, oxygen, hydrogen, represented in their conventional colors of black, red and white. And we learned that in chapter 2, and then we learned how when they are bonded together they make compound and molecules, so ionic compounds and covalent compounds. But matter also possesses energy and is affected by energy. So we will also have to look at energy, and we'll see that matter possesses potential energy and kinetic energy. So remember that energy is anything in the universe that is not matter. And another definition of the energy is, and this is more like for physicists, energy is the capacity to do work. And if work is defined as the action of a force through a distance, like here, you see this man is pushing a big box and is able to push it through a distance, and so is performing some work here because the force is acted through a distance, so work is done. And but for this man to be able to do this work, he needs energy, right? He has to possess energy. And so there is two types of energy, and the total energy of a system is the sum of the potential energy of a system plus the kinetic energy of the system. So potential energy is stored energy, and you may have seen in the previous slide that in the case of chemistry, potential energy is the energy stored in bonds between the atoms. And kinetic energy is the energy of motion. So for molecules, it's the energy that allows molecules to move. So let's look at these two types of energy more in detail. So kinetic energy is the energy of motion. And so, for example, you experience kinetic energy when you are in a car moving down a roller coaster. And if we look at the drawing at the bottom of the slide, there is kinetic energy represented by Ke and potential energy represented by Pe. And so when you're going down the slide, down the roller coaster, you are accumulating kinetic energy and losing potential energy. There is an exchange between the two types as you move down. Another example of kinetic energy is a moving spring. So if you have a spring and it's moving, then it possesses kinetic energy. And if you apply this kinetic energy to chemistry, so the molecules possess kinetic energy when they are moving, vibrating and rotating. All the movements that they are allowed to have are possible because they are possessing kinetic energy. And so potential energy is energy stored for use at a later time. And for example, when the cart is at the top of the roller coaster, and if it doesn't move, here the car will possess a lot of potential energy and has zero kinetic energy. And now if you go down the roller coaster, then you start to lose potential energy because you're going down to the ground. So potential energy here was due to the gravity, the fact that you are high up. So that gave you some potential energy due to the position. And so you accumulate kinetic energy as you gather speed going down. And when you're at the bottom of the hill here and at the ground levels, you have no more potential energy, right? There's nothing to push you downward anymore because you're at the earth level. And at that point, you have a lot of speed and so a lot of kinetic energy. And that allows you to move up the second hill. Another example that possesses potential energy, a compressed spring would possess energy stored in the fact that it's locked into a compressed position. But as soon as you unlock it, it will gather some speed, and the potential energy will be changed into a chemical energy. Kinetic energy. And in chemistry, potential energy is energy stored in the chemical bonds of molecules. So, for example, there's a lot of energy in gasoline and coal and food, and that's why we take food. It's to get energy from the molecules. So we've encountered energy before in the form of thermal energy that we also use to call heat. So heat is thermal energy, and that's the energy associated with the movement of the particles. And we said that the faster the particles move, the greater the heat or thermal energy of the substance. And can you tell me what is the tool we use to measure thermal energy? So think about it. How is thermal energy measured? Using a thermometer, right? And so the higher the temperature, the faster the particles move, and the more kinetic energy they have, the more heat or thermal energy. Because when we say that it is energy associated with the movement of particles, so thermal energy is a form of kinetic energy. And so here you see some ice cube melting. And so when heat is applied to an ice cube, the molecules of water will move faster and faster and eventually have enough energy to change the ice cube from solid to a liquid. And this will happen because if molecules have more kinetic energy, they will move faster and be able to break those attractive forces that hold the molecules in the solid state. And if you have less attractions between the molecules, then you are changing into the liquid state. So the units of energy, the calorie with symbol CAL in lowercase letters is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. So that's the definition of the calorie, and that should recall something about the specific heat of water here. The specific heat of water is 1 calorie per gram and per degree Celsius. So all of this is, coming from the same definition of the calorie. Calories also are mentioned in nutrition facts in food labels. And nutritional calorie is a capital C, CAL, to not be confused with the lowercase c, CL. So these are two different units. So you will have to be careful when you write down your units of calories to pay attention to the fact that you put a lowercase c or a capital C. They mean two different units. And a capital C calorie is equal to 1 kilocalorie. So 1 kilocalorie is equal to 1,000 calories, the small c calories. And so 100 lowercase c calories will be equal to 1 capital C calorie. So that's the relationship between these two units. Joule is another unit of energy, and it's actually the international system unit with symbol capital J. And the relationship between calorie and joules is that 1 calorie is equal to 4.184 joules. So both joules and calories can be reported in the larger units of kilojoules and kilocalories. And so 1 kilojoule is equal to 1,000 joule, right? You replace the kilo by its value, and a kilo is a prefix of value 1,000. So 1,000 joule equals a kilojoule. We already saw that 1,000 calorie is equal to 1 kilocalorie, which is also equal to 1 capital C calorie, or nutritional calorie. We can also use the relationship between calorie and joules and put them both with kilocalories and kilojoules. So if we use the prefix between both calories and joules, we get this fact that 1 kilocalorie is equal to 4.184 kilojoules. So let's go through a learning check to apply those equalities, because you know, as you know already, whenever you have an equality, you can use it as a conversion factor. So how many calories are obtained from a pat of butter if it provides 150 joules of energy when metabolized? So what is given? The 150 joules of energy. We want to change that into calories. So we have a relationship between calories and joules. So we will be able to change the joules using only one conversion factor into calories. And that conversion factor is the fact that 1 calorie is 4.184 joules. And so as always, from an equality, we have two conversion factors possible. So either you have the 4.184 joules on top and the 1 calorie on the bottom, or the 1 calorie in the numerator and the 4.184 joules in the denominator. So here, because we start with 150 joules, and you always start the calculation with your given amount, we will need to choose the conversion factor such that the joules cancel. So we will use the second conversion factor. So the full calculation will look like this: 150 joules times 1 calorie over 4.184 joules. We see that the joules cancel, and the calculator answer is, so you do 150 divided by 4.184. It's 35.85. And here, 1 calorie is an exact number. 4.184 has 4 suffixes. 150 joules has 2 suffixes. So we will keep 2 suffixes. We keep the 3, the 5. What comes after the 5 is an 8. So you round the 5 into a 6 and you drop everything after. So 35.85 will be rounded to 36 calories. Another learning check. A gummy bear is 9.00030 calories, nutritional calories. So how much energy is stored in a gummy bear in units of kilojoules? So again, we will extract the information from the text, and here we have a given value of 9.000 calories, nutritional calories. The question is asking for how much energy is stored in units of kilojoules. So we are looking for kilojoules. We don't have a relationship directly between calories, nutritional calories and kilojoules. So first we will change our nutritional calories to kilocalories, and then the kilocalories to kilojoule. So we will need the fact that 1 nutritional calorie, 1 capital C calorie, is equal to 1 kilocalorie. and 1 kilocalorie is equal to 4.184 kilojoules. So when we are ready to write the full calculation, we will want to start with the given amount, so 9.000 calories, nutritional calories. And you will want to multiply by the conversion factor, the first conversion factor here, coming from the first equality, with the calories on the bottom, so we can cancel the calories with the capital C. So calories with the capital C cancel, and it's 1 kilocalorie over 1 capital C calorie. That's the first conversion factor. Times the second conversion factor needs to cancel the kilocalories. So we will have the kilocalories on the bottom and the 4.184 kilojoules on top. And we see that the kilocalories cancel. So then in the calculator, you do 4.184. All other numbers are ones. And the calculator answer is 37.656. Here, the 4.184 has 4 sig figs, and the 9.000 has also 4 sig figs. So we need to keep 4 sig figs. And so 37.656 will be rounded to 37.65. What comes after the 5 is the 6, so you need to round up. And so the 5 becomes a 6. And so rounded, it's 37.66. And that's the energy in a gummy bear in kilojoules. So to go back to energy here, there is a law of conservation of energy, just the same way that there is a law of conservation of mass. And it states that the total energy in a system does not change. Energy cannot be created or destroyed. And so what happens, and we saw an example of that earlier, is that energy can be transferred from one system to another or transformed from one form of energy to another. And earlier we saw an example of the roller coaster where the car either had some potential energy and zero kinetic energy, and as soon as you pushed it down the roller coaster, it accumulates speed and so kinetic energy and loses potential energy. So the potential energy was changed into kinetic energy and speed. You can think about other transformation of energy from one form to another, like for example, when water is retained by a dam. In the dam there are turbines, and those turbines are being turned when the water is pushing on the turbines. So the turbines turn, and they are related to a big magnet that turns inside an electrical circuit, copper wires, and the movement of the magnet will make the electrons move into the copper wire, and that will create electricity. And that's how you change mechanical energy into electrical energy, for example. And so nutritionists in particular are using the transfer of energy to measure the energy value of food. And they are using what we call a calorimeter. In a calorimeter, the energy or the heat released by burning a food sample increases the temperature of some surrounding water of known mass. And you check the temperature increase, and this will be used to calculate the energy of the energy value of the food. So let's look at this in more detail. So nutritionists, to find the energy value of the food, they burn the food in a calorimeter. And we have a schematic of a calorimeter here. It consists of a steel container that is filled with oxygen. So that's the inside chamber. Uh, it's filled with oxygen because we will burn the food, and for combustion to happen, we need oxygen. This steel combustion chamber is immersed into a measured amount of water. So it's surrounded by water, and we know the mass of that water. And so there is a stirrer to homogenize the temperature of the water, and then a thermometer to measure the temperature of the water. So when the experiment is ready to start, everything is sealed with enough oxygen inside the steel combustion chamber. And then a spark is created. You know, the ignition wires are creating a spark that will start the combustion of the food. And temperature will have been measured beforehand. So, and using this, heat equals m times specific heat times delta T, which is also written as Q equals mc delta T. And this is found in your reference packet. Let me show you that briefly. You have a reference packet here, the first page. The left side, the top left side of the first page is dedicated to chapter 6 with the heat formula, Q equals m delta T SH. And here, while we are at it, there is also the unit energies equalities, you know, the calories and joules, the kilocalories and nutritional calories. And there's also the food type, the kilocalories per gram per food type. So this is what nutritionists have been able to measure over time by doing many experiments. So let's go back to our calorimeter. So nutritionists will use this equation of heat equals msh times delta T, where m represents the mass of the water. It's not the mass of the sample, it's the mass of the water that surrounds the steel chamber. We know its mass. The delta T is the temperature difference that water will experiment. So we took the initial temperature, and then the food was starting to burn. And all the while that the food is burning, the temperature of the water will increase. And so you will reach a point where you will get a maximal temperature, and that's when the food has been all burned. So delta T is the maximal temperature that water reached minus the initial temperature of the water. And SH or C is the specific heat for water, because here the mass and the temperature change are for water, so you need the specific heat of water for this formula in this case. And so C is 1 calorie per gram and per degree Celsius in the case of water. So by calculating the heat gained by the water, you will know the heat that has been released by the food sample. And this way, nutritionists know how much energy was contained in the food. There was a transfer of the heat from the food to the water, and we were able to measure the heat that was absorbed by the water, and that because energy is not lost or created or destroyed, then that tells you the heat gained by the water equals the heat lost or released by the food. And so this way, nutritionists have made a lot of experiments and found that the energy or the caloric values of food are the kilojoules or kilocalories obtained from burning 1 gram of a carbohydrate, a fat or protein. And so carbohydrates always release 4 kilocalories per gram, or in kilojoules, it's 17 kilojoules per gram. Fat always releases 9 kilocalories per gram, or 38 kilojoules per gram. Proteins release 4 kilocalories per gram, or 17 kilojoules per gram. So you see that depending on the type of food, the energy value is different. And so we can use those caloric values to find out how much energy is contained in some food. For example, let's go through this learning check and see how this can be used. A cup of whole milk contains 12 grams of carbohydrates, 9 grams of fat, and 5 grams of protein. How many kilocalories or nutritional calories does a cup of milk contain? So we want to extract the information given in the text, and here we have 12 grams of carbohydrate, 9.0 grams of fat, and 5.0 grams of protein. That's the grams from 1 cup of whole milk. So whole milk is a very complete food because it has all 3 types of food: carbohydrates, fat, and protein, if it's whole milk. And so here the question is asking for how many kilocalories does this cup of milk contain. So we want the total number of kilocalories when you are eating 12 grams of carbohydrate, 9 grams of fat, and 5 grams of protein. And so according to the previous slide, we know that 1 gram of carbohydrate releases 4 kilocalories, 1 gram of fat releases 9 kilocalories, and 1 gram of protein releases 4 kilocalories. So here they are already written in the form of conversion factors, because the givens are grams of each type of food. So we will use those equalities with the kilocalories on top and the grams on the bottom, because this way we will cancel grams of food. And so, for example, 12 grams of carbohydrate multiplied by 4 kilocalories per gram of carbohydrate. So that's 12 times 4, 48 kilocalories that will be given by the 12 grams of carbohydrate. And we see that the grams of carbohydrate units cancel. Same thing with the fat, so 9.0 grams of fat times 9 kilocalories per grams of fat. The grams of fat cancel. We do 9 times 9, it's 81 kilocalories released by the 9 grams of fat. And then the 5.0 grams of protein times 4 kilocalories per grams of protein. The grams of proteins cancel, and we obtain 5 times 4, 20 kilocalories of energy from the proteins. And so 20 with 2 sig figs here, because 5.0 had 2 sig figs. And then the question was asking for the total amount of kilocalories. So you want to add these 3 amounts together. 48 plus 81 plus 20 is equal to 149 kilocalories. We need to keep 2 sig figs because all the given amounts of grams were having 2 sig figs, right? 12 has 2 sig figs, 9.0 and 5.0 have 2 sig figs. So let's round 149 into 2 sig figs. So we keep the 1, we keep the 4, and what comes after the 4 is a 9. So we need to round the 4 into a 5. And then we need to add 0 to show that this 1 it was in the hundredths place, the 5 is in the tens place, and then 0 in the ones place. So 150 kilocalories is the rounded value with 2 sig figs. And the value in nutritional calories is the same, because 1 kilocalorie is equal to 1 capital C calorie. So it's also equal to 150 calories with a capital C.